Welcome to the next lesson of Learning Image Analysis, where we continue with iterative refinement of a segmentation. So our image today is bimodal alpha titanium. What we have here, if you look at this image, the alpha is the dark grains and these dark alpha laths, and the beta is the bright boundary around them. So what happens is when it's heated, it likes to be in this beta phase, and when it's cooled, titanium prefers to be in the alpha phase. So if you take a piece of titanium and heat it up, it'll all turn to beta, and then when you cool it down, these grains of alpha will nucleate and grow. And so the alpha will precipitate out of the beta and build these grains. If you then take that piece of metal and heat it up again, of course the alpha grains will start to melt on their boundaries. But before they completely melt, if you then cool it down, you'll get secondary alpha formation here where the new beta was. So that's why you have these large alpha grains and these smaller alpha laths in the middle. This is primary alpha and this is secondary alpha. And of course the speed and the temperature to which the speed with which you heat up and cool down and the temperature that you bring it to determines the size and the shapes of these different features. And of course, you can imagine that these different parameters, how much alpha is in primary and beta, and secondary alpha, and all that kind of stuff, has a pretty strong effect on the material properties of the metal. So over the course of 2 lessons, we're going to separate the alpha from the beta, and then we're going to separate the alpha into primary and secondary. So our lesson today will just be percent alpha versus percent beta. We're going to find the beta and the alpha. And in the next lesson is when we'll divide the alpha up into primary and secondary, and then we can get a primary alpha grain size and the fraction percentage between those two. So we're learning images for today. Because we're doing iterative image segmentation, we're going to be okay with our first segmentation pass having errors in it, because we know in later iterations those errors are going to be fixed. So it can be a little stressful sometimes if you're a perfectionist to not have your segmentation look perfect when you make it. But if you get over yourself and you realize that certain errors can be fixed, then you will have the ability later to go back and fix those errors. And then, of course, as you're fixing errors, you need to know what types of filters, what types of segmentation methods should you use in order to be able to target those errors, in order to be able to achieve the result that you want. And most importantly, be willing to experiment. You're not always going to be able to know just off the top of your head exactly how a particular filter is going to interact with your image. I'll also talk about how to double check your work, see if there's anything wrong or any redundancies, inefficiencies in your recipe that can be cleaned up once you've got a final result. We'll also talk a little bit about memory management, how to make your recipe memory efficient. So let's see what we can do with this image. Obviously, the first thing we want to try to do is clean. We have some fine variation in here. And so we'll start with our non-local means filter. And let's see how well this works. Removing just a little bit of the fine detail that we might want to keep. So if we reduce the strength of the hair, and it's still keeping a lot of this beta edges here, so we'll be fine with the strength of 0.15. Now, of course, we want to save this cleaned image away because we'll be going back to it a lot. The whole point of this lesson is that we're going to be doing different segmentations and combining them all together. And we'll want to start with this cleaned image each time. So rather than having to rerun the non-local means, we'll simply save our cleaned grayscale image away. So let's now look at separating the beta from the alpha. And it looks like the beta is pretty uniformly brighter than the alpha. So we'll try just a basic bright threshold. We've got two nice peaks here, and see what we have. So we're seeing a couple of things. First is that, of course, if we go too low, we start finding pieces of alpha as beta. But if we go too high, we start losing some of this fine structure here that we want to have selected. Right? We would have to go right about here to get a lot of this fine structure. That's got a lot of this really broad alpha pieces. So how about we try being conservative with our basic threshold, and then in a second step we'll add these fine pieces in. So around something like that looks like a good value. Alright, so now if we call our denoised image, and when I'm trying to find fine structure that has different levels of gray in it, they're not all uniform, the first thing to turn to is an adaptive threshold. So here we're finding beta. If we want to bring our percentage up enough to find some of this tight stuff, we still have some broad pieces of alpha that were found. So there might not be a way to get around that. But at least this way, this broad alpha that we're finding isn't necessarily all the bright stuff. It's simply the bright alpha that's brighter than its surrounding features. So maybe we can take a basic threshold here and subtract this dark stuff away. So we'll again try our memory image 6 and look for as much alpha as we can get without overlapping or removing too much of that fine beta there. Okay, and what does it give us when we subtract these away? Call memory image 1 and subtract. I'm still not happy. We've still got this broad stuff here. So, how can we get a better selection? How can we get something better than this adaptive threshold? And what we see is that these edges are found with our basic threshold, or excuse me, our adaptive threshold. It's a side effect of also finding this tight beta. But there is a way to find features like this without also finding these edges. And that is using the bright texture filter. So let's remove a lot of this and try our bright texture filter. Say we set a window of 3. Okay, and so we're finding these tight edges, but we have a little bit of noise here in the center. But this edge here is completely absent. So this is a lot better than what we had with just the adaptive threshold. So 5. If I look at these different numbers, we want to find as much beta as possible without finding too much of this alpha. 7, 8. How about we stick with a 5 for now and do a basic threshold on this preprocessed image. And so, bright beta features. But of course, a bright texture doesn't find large chunks like this. It only finds things that are below this window. So how about we try to add these bright chunks back in? And we'll notice that they actually are a lot brighter, these large pieces, than the fine things that we're having trouble finding with just a basic threshold. So if we try just to find the really big obvious pieces like this without grabbing any of this alpha. Okay, and how about we add it to the basic threshold here? Memory. Set this as a companion. We'll set this in memory. Call back and union. What do we have now? Okay. We might want to be a little bit more aggressive with this bright or basic threshold here. Alright, that's looking pretty good. But we still have the issue of these tight pieces in here. Well, we don't want to reject on size, even though they're smaller than a lot of the beta, because there are legitimate tiny pieces of beta in this image. And we can't just subtract based on a basic threshold. We saw before that getting a basic threshold high enough to select these darker pieces also tends to obliterate some of this finer true beta. So what can we do? Well, we can notice that a lot of this finer beta that's dark is connected to bright beta. So that tells us that yes, these individual pixels might be darker, but the average grayscale intensity of this whole feature will be higher. If I zoom in here, you see we have some dark beta here, but the whole average grayscale intensity of this feature is pulled up by these bright things that it's connected to. So rather than just subtracting pixel by pixel, we can do a reject features, rejecting entire features based on their intensity mean. Now, before we do this rejection, though, we should notice that some of these finer pieces of darker beta aren't quite connected up the way they should be. So we'll need to remedy that before we can do our reject features. And we'll do that with just a simple dilation. If we dilate by 1 pixel, we can get some of these joins to happen. But that gives us another problem. It shows us that some of this darkness around the bright beta actually gets found, and that's going to drag down our average grayscale intensity. So I have to do a little bit more pre-processing just before we can really go forward with our rejection. So how would we do this? How would we clean away this dark stuff? Well, if you want to remove pieces of dark selection that are adjacent to bright selection, I use generally an adaptive threshold for that. Specifically, we're going to use it as a mask. So we'll feed this segmentation into the adaptive threshold, and then look within it for pixels that are brighter than other pixels also within the mask. So if we set this away, say memory image 4, and now call back the noise reduced image, an adaptive threshold with memory image 4 as the mask. Okay. And we'll grab all the bright stuff, and 100 gives us what? Now we're still not collecting things that we wanted to collect. So if we lower our amount here all the way down, and of course we find all the edges, but see, I'm watching this boundary and this piece of beta. I want to make sure the boundary is removed, but the beta is not. And that looks like a good value right there. Okay. 9, about that. Okay. And now this is a segmentation that we'll use to do our reject features on to try to remove these pieces in here. So in MIPAR, to do a reject feature based on grayscale intensity, you need to have a grayscale image in the companion. So we'll say set this as memory image 3 isn't being used, and call the original, set it to the companion, and now call back memory image 3 and reject features. And let's do some measuring. Excuse me, intensity mean 105, 90, okay, 109. And this stuff here is 159, 158. How about we find some more isolated small pieces? 125, 93, so 125. So it appears that there's no hope for this dim feature here, but so be it. It can't be absolutely perfect. But looking at the segmentation overall, I'm actually pretty happy. Okay. So now we have our clean beta segmentation. But we should go in and do some optimization of the recipe. So you see I've got some extra memory images here that I'm using because I didn't want to overwrite memory image 1. I didn't know if I would need to call it back. But now I know. I call memory image 1 and I don't use it again. So instead of setting memory image 4 here for our mask, I can set this as memory image 1 instead and change our mask. And now that's a whole copy of our image that's no longer needed to be saved in memory. So that's going to help us out a lot. And again, we don't need to set to memory image 3. We can set to memory image 1. So set memory image 1. Instead of calling memory image 3, we'll call memory image 1. Okay. And now our recipe is a lot more memory efficient. But we can do a little bit more. If you see here, we take our basic threshold and we set it to memory image 1. Then we call memory image 6. Do another segmentation, set to companion image. Call memory image 1 and do a union. We can eliminate the need to use this memory image if instead of setting our companion, setting this into the companion, we set this into the companion. So if I take our basic threshold here, set it as a companion, I don't need to do this sort of manipulation. All I need to do is simply union our two segmentations together. So again, that saves us from having to set memory image up one up here. And for this recipe, it doesn't matter so much because we end up needing to use this memory image slot anyway. But in a more complicated recipe, eliminating this early call might help you on down the line. Now, say, for instance, that this operation here required a companion image. Maybe it was more complex than just a simple basic threshold. If for some reason we needed to set the companion image in the middle here, well then we're no longer going to be able to store this just in the companion image above. But you can still achieve the same effect if this doesn't require a companion image inside of it by simply moving it afterwards. So what we would do is have our operation, take this and set it as our companion, and now do this afterwards. So memory, call memory image 6, bright texture, 5, do our basic threshold of 18, right. Okay, and now we have our union. Now, if both of these are more complex and require companion images inside of them, then you're stuck. Then you have to take one of these and save it in memory and call it back later. Okay, so now we have a 17-step recipe, a lot shorter than the one we were using above. And that's another thing. If you're not switching memory images around and doing all this juggling, it actually makes it easier to read the recipe itself. There's less steps, there's less things that you have to hold in your head to understand how it's operating. Now that we have what looks like our final segmentation, let's go back and make sure that we're not doing anything silly. Make sure that we're not doing the same thing multiple times. Say we've got two subtractions that both end up subtracting the same thing because the same thing got added again with another iteration. That kind of silliness. So what I'm actually going to do first is visualize specifically what is being removed by this reject features. We'll set that to a layer, dark features, rejected. And we'll do the same thing with this adaptive threshold here. Adaptive threshold with dark features. And we'll also set our dilation here as a layer after dilation. And now we have our two addition steps, our basic threshold and our bright texture basic threshold. So this one will be bright texture basic threshold, and this will be our regular basic threshold. Okay. So if we start just by looking at our two additions, are they redundant? And in this case, no. It's simple. We've got this first one to collect fine stuff. We've got this addition here to collect big, bright stuff. But if this recipe was more complicated and say halfway down the recipe we found another addition that happened to redo what one of these was doing, then maybe we could go back and look at the recipe and figure out how to remove some of that redundancy. Okay. And now these are the dark features that are being rejected. You can see these right here. Of course, they are added by the bright texture. What we might have been able to do is remove this rejection step if we could somehow remove this bright texture. But we know we can't because we need both of these together. And we've got this dilation part that's necessary for making sure that our features are well joined before the dark features. Then we've got our adaptive threshold here. Okay. So I don't really see anything that we can remove from this recipe to make it more efficient. But you might have, in the course of building a more complicated recipe, say you're up at 30, 40 steps and you've been working for half an hour on it, and there's some work that gets duplicated. But for our purposes, we'll be happy with what we have. So let's remove all of these layers here and set our final project features back to what it actually is. Okay, and this will be our beta. We'll change it to purple. And now invert our segmentation, and this will give us our alpha. And let's make this green a little bit darker. And now we can measure this image, particularly area fraction. Beta of 13.2% and alpha of 86.8. That's it for this lesson. Next time we'll do some large-scale segmentation manipulation to take our alpha segmentation and separate it into primary and secondary. So I look forward to working with you then.